Okay, good morning. Let's get started with the new week of lectures. Okay, so today we'll try to finish the convolution. So basically the example we started from previous lecture, let's finish that. So the question is to convolute the two boxes. All right. So as we let me see if I can use my as first step, you change this to tau. And the second step is to obtain g of t minus tau, or in other words, basically g of negative tau minus t. So this is a step that's critical. Okay. Red color. Let's use red color here. Okay. So when you obtain this step, as we illustrated in the previous lecture, the two edges, right? The two edges of this g of t minus tau, right? The two edge, they are basically one is -1 plus t, another one is t. Right? So don't forget now that basically you go back to your convolution. Your convolution is about multiplication of the two graphs. You multiply the two graphs together and then you do the rest of the integral. So the integral will only be meaningful if the multiplication of two graphs is non-zero, right? So that's your key point. So essentially you need to identify under what condition the multiplication of the two graphs is not zero, right? Now, so basically what influence, right? What influence the multiplication of the two graphs here? Now you can see here, I mean, this graph is not moving. This graph is always there. And this graph is actually a moving graph because if the t is different, then this box will be at a different location, right? In this graph here. So at a different location of the box will result in a different multiplication or what we call patterns of overlap, right? So so basically, let me write down the comments here. So different value of a t or a different location of t of negative tau minus t, right? So different location of this box or this graph results in different patterns of overlap between this f of a tau and t of a t minus tau. So this is the key. You have to, sometimes you have to manipulate a little bit, okay, in order to figure out all the different patterns of overlap, okay, between these two graphs added here. So for example, right, so let's take a look at what will be possible patterns of overlap. So let's just observing it first. Okay. So I'm gonna maybe plot. I'm gonna plot the g of a t minus tau in the same graph as at here. Okay, just for illustration purpose. Okay. So one type overlap is this, right? So this box is completely on the left side of this vertical axis here. And this is a pattern, right? This green one is one pattern because obviously, right, these two under this pattern, there's no overlap at all. So maybe let's just summarize now. So pattern number one, this is your f of a tau, and this is your t of a t minus tau. Right, this is pattern number one. The edges will not change, right? Still negative 1 plus t and t. Okay. So this pattern here, so pattern number one, no overlap. If there's no overlap, that means the convolution will be 0. Okay. So now you let us next question. Next question, back to this comments here, right? See, we said different t value, right, results in the different patterns of overlap. So then for this pattern here, what range of t to give you this pattern number one, right? That's the next question you need to ask at here. Right? So essentially, what range of a t gives this pattern? Okay. Not all range will give you this, right? So this is the question, right? You're gonna ask this one here. So then you look at this one. Okay, basically, what value of a t to ensure that this box will never overlap with this f of a tau? And of course, as we said, it's always on the left side of this 0 value here, meaning this edge t has to be always less than 0, right? So that's, as long as this edge is less than 0, then the other edge is definitely also on the left side, right? That's guaranteed. Okay. So that gives you, based on the observation of the edge compared to some other reference. So essentially, for this particular step here, you need to compare the edges of g of t minus tau with some kind of reference. So these comments not necessarily only apply to the pattern one. It actually also applies to other patterns, okay? Yeah. So here I'm comparing this edge with this 0 value here, and then that's guaranteed, right? This convolution is 0. So there you go. So that's your pattern number one, happens when t is less than 0. Now, sometimes you say, should I have an equal or not equal? Actually, it doesn't matter. You can put an equal sign here, or you can put an equal sign to the next range, okay? Because they're going to be a continuous range, right? Yeah. which is fine. Good. So that's your pattern 1, right? So now let's look at other patterns. Again, we're not changing f of tau. F of tau is always here. So what's changed here, right? What's changed here? Remember, what's changed here is what? Is this moving box g of t. So basically, it's moving to the right. How does it moving? Because the t value, you can change the t value. You give a different t value, and this box will start to shift to the right. Okay, it can move over here, can move over here, move over here, right? So continue to move as t go to infinite. Okay, that's how this box can be shifted. So as you can see, this is the first pattern. Now, second pattern is this, right? So basically, this box is overlapping both sides of the coordinate system. Okay. So now, actually, maybe before I write it down, pattern number 2. So what do you think the third pattern would be? 0 to 1. So basically somewhere here, right? So it's completely within that f of tau boxes. That would be the third pattern, right? Because you can see as it's moving within the box, right? There's the same, basically the same multiplication. What would be the third, the 1, 2, 3, the fourth pattern? It'll overlap this range here. And the last pattern, completely out of range and become 0 again for the multiplication, right? No overlap again, right? So that's how you can identify the patterns, right? So the second pattern will be over here. So let's draw this second pattern. So sometimes the drawing needs to be a little bit accurate so that reflects the actual scale of this original graph. Okay, that's why when you do the drawing, I encourage you to use a ruler, right, to do this. So this is the second pattern. Let's write on here pattern number 2. And for this pattern, right, you need to identify where does the overlap happen. So overlap happens now, right? So essentially over here, you ask the question, where is the overlap? Where is the overlap? This question, answer to this question actually give you the integral limits because you're integrating. You're integrating the multiplication of two graphs. And you don't need to integrate any 0 portion, right? You only integrate the overlapped portion. So obviously in this part, the overlap happens over here. And where basically means is tau between 0 and where? Right? Where does it happen, the overlap? 0 to this edge, which is t. So that's the answer to the where, and this is your answer to the integral limits, right? So 0 to t. So now your next question is, within this 0 to t overlap, I'm multiplying the two graphs here. What is the value for f of tau between 0 and t? Value for f of tau between 0 and t is 1, right? Because the graph here is 1. What is the value for g of t minus tau between 0 and t? It's also 1. And then d tau. Okay. Right, so you're multiplying the two graphs. Both graphs' value between 0 and t is 1. So you replace, what you're replacing? You're replacing this f of tau, and you're replacing this g of t minus tau with 1 and 1, and that gives you t. And the next question, as we did in pattern number 1, right, is this question. What range of a t gives this pattern. Because you're shifting t, right? You're shifting to the right. And there got to be a certain amount of the t that results in this pattern of overlap. So this question here is you got to stick to the pattern, okay? The pattern here basically means one edge is on the left side and one edge is on the right side of this zero location. So basically means this -1 plus t needs to be less than 0 and the other one needs to be greater than 0. So this guaranteed this little box G is covering both sides of the x-axis, okay? And that gives you a range of t that's greater than 0 and then less than 1. So this is continued from the previous one. The previous one, t less than 0, and now it's a t greater than 0 and less than 1. So what I'm trying to get is, right, you can see there's a connection, huh? When t is less than 0, you've got this convolution to be 0. When t is within this range, you got the results of the convolution to be t. So that's pattern 2, right? So every step, we ask 2 questions. The question is, where is the overlap? And what is the range of the t to give you this overlap? So now let's look at the pattern number 3. So pattern number 3, as we shown here, you have the box right now is covered within the box f of tau. Because f of tau, the length of the box is a little bit longer, right, than the g of t minus tau box. Now, of course, the edge is not changing. It's still -1 plus t to t for the box g of tau, g of t minus tau. So this is a pattern number 3, right? Pattern number 3. So again, ask the question, where is the overlap? Right? Where is the overlap? Overlap apparently happens, right, underneath this small box. Because that's the only portion that give you non-zero multiplication of f of tau times g of t minus tau. So your overlap happens from from -1 plus t to t, right? So overlap, let me maybe write it on, let's see. Overlap occurs within tau to this and t. So then your integral of the convolution is this, okay, limit. And again, you're multiplying f of tau n times g of t minus tau. Okay, you multiply this. And within the overlap, both function value is 1. That's pretty straightforward. Then you get very simple integrals. So t minus -1 plus t, and you actually get a 1. Okay. So as a matter of fact, you can actually verify, does a 1 make sense? Because you see right now, what is overlap? This is overlap, right? And you're integrating this, basically you're getting the area for this overlapped region. And the area of the overlapped region is 1 times 1, which is 1. Right? So that makes perfect sense. So the next question is, right, what range of t to give you this pattern of overlap? Okay, yeah. So this part here, sometimes, you know, there can be a little bit of mistake here, but you have to basically stick to the principle. You compare the edge, and here compare this edge, okay, with what? With the reference. What are the reference? For example, this is a reference, right? Because you want a t to make sure the t is not crossing the 2 value. You want a t to make sure the t is less than 2. Okay, so you can put a equal sign, that's fine, right? That's one reference. And the other one reference is you want the -1 plus t, this edge here, not gonna be on the left side of the axis, left side of the vertical axis anymore. You need this edge to be on the right side. So you need the -1 plus t edge to be greater than 0. So these two should be suffice. So you get t greater than 1 and then less than 2. So you get a continuous t range. You see, right? The t is changing from 0 to 1 and then 1 to 2. Right? So essentially, the current t range will ensure that this convolution is under this overlapping pattern and give you the value number 1. That's pattern number 3. So pattern number 4. F of tau still the same. So this time your box, right? This is g of t minus tau, right? Overlap with f of tau with this pattern now. So that's the fourth pattern. So under this pattern, again, ask the same 2 questions. First question, where is the overlap, right? Okay, so that is overlap here. Where is overlap? Basically, the question is, where is the non-zero portion of overlap? Okay, so this answer to the question will give you the integral limit. So the integral limit here, so again, so this tau between -1 plus t to 2. So you get -1 plus t to 2, then f of tau times g of t minus tau d tau. Again, within this range, both function value is 1. So the result is 3 minus t. So second part of the question, what range of a t or what value of the t to give you this current pattern of overlap? You compare the 2 edge of the gt minus tau with some reference. So I think the important reference is this one here too, right? So you need your t, this range, this edge to be more than 2. You also need the other -1 plus t edge to be less than 2. So this relationship will restrict this box to be strictly over here. Right? So that gives you a t's range, which is more t more than 2 and t less than 3. So now you can see, okay, within this range of t shifting, and then you get a convolution value 3 minus t. Okay, so last pattern, number 5. Now the box is completely shifting out of the range. No overlap anymore. Okay, so your convolution back to 0. Back to 0. Now the question is, what range of the t give you this type of a pattern? So you compare -1 plus t to more than 2, which give you t more than 3. So that gives you the convolution to be 0. And that's it. So there are technically 5 different patterns, right? So finally, you can summarize your convolution f of t with g of t. Start with a 0 when t is less than 0. So again, the equal sign, I'm not going to be too picky, but the equal sign, sometimes you can neglect this equal here, but then you put an equal on the next range. That's fine. Okay. Yeah. The second value is t when t is greater than 0, less than 1. And then 3 minus t, and then 1 when t is between 1 and 2. 3 minus t when t is between 2 and 3. Finally, we get a 0 again when t is more than 3. Okay. So this is a results convolution, right? Graphically, you're solving it step by step by examining the overlap, by examining the range of t to give you this overlap, right? And you get this total results of f of t convolute c of t. And then you can actually plot. You can actually plot this graph, this piecewise function here. If you plot it out, so this is f of t convolute g of t, and you get a trapezoid type of things. So this is 1, this is 2, this is 3, and this is 1. First part is 0, second part is straight line t, right? This is t here, this is 1 here, and this is 3 minus t. Okay, so that give you a, this is more of a, I would consider this is more of a, on a challenging side of the convolution, because there are many more type of patterns involved at here, right? Rather than maybe sometimes only 1 or 2 patterns, that's it. Right? This one has like a, technically for non-zero part is 3 patterns. In the assignments, actually, in assignment, I think in assignments or something like this, there's even one question that's even a little more complicated than this one here. Okay, but doesn't matter how complicated. I want you to stick 2 points, right, in your head. You're shifting the second function, g of t. Okay, you're shifting it. When you're shifting it, you keep 2 questions to ask yourself. What is the pattern overlap? Right? You got to stick to the pattern. Pattern means different, right? When you multiply the 2 graphs out, they're different. What is the pattern overlap? What is the range of t to give you this pattern? As long as you can answer this question correctly, then you can get the graphical approach correctly. So I do have a MATLAB simulation actually that you can actually play. I can upload the code. So this shows you an example. You know, see here, it's a moving t value, right? And it's changing here, and then until it's in this range, you're at 1 constant. So exactly the same process as we have just done. Okay. As it's moving out of this range, it's dropping down. Back to 0. Okay. So feel free to study the code, and you can even run the code, okay, slowly, step by step, and see what happens at each step. What is the value of the t, right? What is the value of the convolution for that range? Okay. Okay. Any question on the convolution? Yeah. So you do need exercise, of course, and trust me, it's not that difficult, especially for the graphic approach. It's about to keep a clear head and identify for some complicated functions, piece graphically, right? Okay, so if there's no question, let me introduce you a new concept or new function called unit step function. So there are 2 important functions I need to introduce. One is called a unit step function, and the other one is called the impulse function. So let's look at the first one, unit step function. So I'll give you the definition first. Now we typically use u of t to represent this unit step function. It's more of a convention. You don't actually use any other symbols rather than u of t in this class or even in many other classes to represent the unit step function. And it's defined as, okay, when t is greater than or equal to 0, it's 1. When t is less than 0, it's 0. So that's u of t. And graphically, what it means is 0, 0, 0, and then at the t equal to 0 location, you have a jump. A jump to 1, and then continue with 1. That's how the name is obtained, a unit step. A step up and maintain at a unit value 1. And sometimes this is also called Heaviside equation, a Heaviside function. It's named by a mathematician with the last name of Heaviside. Now, if you look at different textbook, okay, I don't want to confuse you too much. Some types of book, what they do is they don't define the value at t equal to 0. So basically means, for example here, right? I said when t is equal to 0, the value is 1. Okay. But in some other textbook, they don't really define that. They just, when t is greater than 0 is 1. When t is less than 0, it's 0. So t equal to 0 location is not defined. It's more of a, thinking of instead of a like sharp jump, more of a just a very smooth transition at it here. Okay. So it won't affect the computation though. Okay. With this t greater than 0, as I define it at t equal to 0, that's fine too. There's no mistakes in terms of any future calculation. It's just to give you a heads up. If you look at some other reference, especially Wikipedia, you'll see that t equal to 0 is not really defined. Right? So what's the benefit of this unit step function? Okay, so that's essentially what we want to figure out. And there's so many benefits actually. So for now, I'll give you a benefit, and for future system response, system calculation, we have other benefits that I can show you, okay, when it comes to unit step function. So let's look at an example here, okay, and to show you the benefits. So let's say given a function g of t. So this function is defined as this graph by the graph. And this portion of the graph is e to the negative 2t. I think we have seen this. When we do the convolution, we use this function, right, to convolute other ones, the other function. It's a causal function, meaning when t's value is less than 0, you don't have anything, it's 0, right? Yeah. And when t is greater than 0, the function takes value from e to the power of negative 2t. So how am I going to relate this function to this unit step function? Let's back off a little bit, okay? Back off a little bit, meaning if I just graph e to the power negative 2t, then what does this graph look like? It looks like this, right? Because there's no restriction. Okay? At t equal to 0, it's exactly the same value, which is 1. Okay? However, right, the graph of e to the power negative 2d, technically no restriction. It can go beyond to the left side. So in the previous example, right, when we described the function g of t, and we described it as a piecewise function. So this is called the piecewise function. right? Define it like a 2 pieces. So now the question here is, can I actually, instead of write the function as a piecewise function, can I write it as if like a general writing of a function? Remember, you typically write a function here, let's say f of t equal to t squared, right? That's a single expression. There's no pieces, 2 pieces or 3 pieces, just 1 piece, right? T squared. So the question here is, can I make use of this unit step function to rewrite this piecewise function into one single expression? Okay, so that's the objective. So to write g of t into one single expression. Okay. So let's look at how g of t is generated here. So g of t is basically part of this e to the power negative 2t, right? It's only taking this portion here, right? It's only taking this portion, and this portion is taken away. So how can I take this part away then, right? So if I want to take this part away, I guess I can multiply this portion with a 0 value. Then nothing exists on this part. Then how can I keep this part without changing it? I multiply this part with a what value? 1, exactly. So that is exactly what this unit step function is doing, right? So this side is 0, this side is 1. So if you multiply this e to the power negative 2t with the unit step function here, you're essentially get rid of the left side and then keeping the right side without changing its value. So that's one benefit of this unit step function. So now g of t basically equal to e to the power negative 2d times u of t. So in other words, the piecewise writing, right? Then you write 2 piecewise is being taken care of by the inherent definition of the unit step function u of t. And what's even better is the t's range, right? You don't have to worry about t's range anymore. You can just keep it as a negative infinite to positive infinite. Because u of t will naturally take care of the cutting and the keeping. Right? So that's the benefit of u of t, right? So let's take a look at another benefit of u of t here. Right? So let's say this is another function f of t, and this one is a function that we just used when we do the unit step function, when we do the convolution, right? So this convolution, we call it the g of t box, but now I call it f of t. Okay. So same thing, if you write this box piecewise, then you probably had to write the 0 when t is less than 0, and then as 1 when t is between 0 and 1, and then 0 again when t is greater than 1. Right? So you're gonna have to write 3 pieces to describe this box function. So my question here is, can we make use of unit step function to write it into one single expression? One single expression representing this box using unit step function. Okay. Yeah. Okay. So you had basically a little bit of observation in it here, and then you probably will have it there. So, but let me give you a little bit of hints. So I'm going to plot u of t first. This is u of t. So at least I actually can say that from 0 to 1, and these two is equivalent. Right? Except that after t equal to 1, you still have a continuation at here. And then this one go back to 0 now. So the question is, how can I get rid of this part, right? So I guess I could already have some ideas. Or f of t must be u of t minus something. Minus something. So what should it minus, right? So let's graphically, if I want to take this portion away, this is 1, right? This portion is 1. What should I minus? You should minus that. Forget about the expression here, just graphically here. Graphically, yes. Oh, good. You already tell me the answer. Excellent. So let's hear from this. Yeah. Yes, you want a reflection of UT. Okay. Burb's answer is right, but let's say reflection of u of t is what? Is, let's use the green color, is this, right? So if I reflect it, this is the u of negative u of t, right? Yeah, the green one. Okay. But can I just simply minus the green one? If I minus the green one, then I'm also getting rid of this part here, right? I don't want to get rid of this part. I only want to get rid of this part here. So that's where the answer from the verb. You have to do what? You have to shift this one to the right. So shift it to the right. Shift the flipped u of t. So this is a negative u of t minus 1, right? So shift it and then you subtract. That you give you the actual box defined for the f of t. Okay. Yeah. So I want you to understand how this arrived, and then I also want you to actually now sort of make it a more of a memory in your head. Whenever you see u of t minus 1, there should be a box of a length of 1 coming into your head. It's a box. It's this box here. Okay. So what if I change this to, what about if I have a function g of t equal to u of t minus u of t minus 2? Yes. Exactly. Right? That's what I want you to, as a reflection, now in the future here, you can establish what type of box we're talking about here. Very good. The reason I'm trying to make you memorize this is because, right, we can use this box as a cookie cutter. Okay. So let me maybe give you another function. Let's say call this as c of t. Let's see, now this is u of t minus 1 to u of t minus 3. So this is a new function. It's a new box. So where do you think this box is going to be now? You look at this edge. This starts at 1, and this box ends at 3. So 1, 3. And the length of the box is 3 minus 1 is 2. So this edge here is 0, and this is 2. The length is 2 of the box. So it doesn't matter how you change the u function, right? So now this time you know what the box will look like, what's the length, where the location is the box. Okay. So how can I make use of this cookie cutter now? For example, right? Let's say, give you an example here. Here is the function f of t. Okay, so this function of f of t is basically a portion of a straight line. Other than this portion, every other locations are 0. So I want you to write down an expression for this piecewise function using one single expression by making use of the unit step function. Okay, so this function, as I said, it's basically a portion of this straight line here. And the straight line, what's the straight line equation? You can identify easily because this is 2 and 2, this is 0. So straight line is t, right? It's t. So how can I cut that portion out? By making use of the unit step function. What do? This is where the function is getting used for, right? The cookie cutter here. Those are, I call it cookie cutter. You can multiply any other function with this cookie cutter, then you end up with just a portion of that function. So I'm multiplying, which one should I multiply? Because this is 0 to 2. So I guess which one should I multiply? This one, right? So if I multiply t with this, and you're cutting that little bit out of this original function t, and you end up with just the red part. That's how the cookie cutter works. So a quick exercise, let's see. All right, so let's just suppose your function is this location, a segment of this t, but is within this part. And if you apply the same principle, then this function, let's call this is w of t. Then w of t now equal to t times what cookie cutter now? Right? Yeah. So this is the a unique things benefit to part of this unit step function that save you some writing in terms of the piecewise function. Okay. Just one more example, then I can call it a day here. Okay? And you know what? It's already 9:50. Well, anyway, so I think that's pretty much the idea of a unit step function. And I'll show you one more example, then we can talk about other functions. Okay. Any questions? Feel free to come over.